तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we introduced you to the map method of Boolean simplification. We drew a corner map, which is a graphical representation of a truth table, filled this graph with ones corresponding to the cells for which whose minterms had a output true, and zeros. Of course, we didn't mark zeros to avoid cluttering of the map. Wherever we did not mark a 1 in the map, the entry was a 0, which was purposely left out so that the map doesn't get cluttered. The object is to identify groups of ones as large as possible, of course with the satisfying the adjacency rule, and remove or knock off as many variables as possible, so that by repeatedly doing this we can get a simpler representation of a given Boolean function. So we will look at a few more examples today, some special cases and all that. We will take an example of a map like this. Four variables. We will call these variables A, B, C, D. Let us say this map has ones in the following cells. This is the pattern of ones. That means this is a function which is expressed as sum of the following minterms. This is minterm number 2. So let us start this from here. 0, 1, 2, 3, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right? This is the map. Now, the idea is to group adjacent ones with as large groups as possible, keeping in mind the group should be as large as possible. If we have a smaller group which can be totally submerged the larger group, we should not consider the smaller group. And we have to make sure that all ones are covered. And we do not mind one being covered more than once. These are the rules. Make as large groups as possible, keeping in mind the adjacency rule. Make sure that all ones are covered. Do not worry about combining more than one, a given one more than once. And so there are only two groups of groups of two only in this possible. In this map only groups of two are groups of two ones are only possible. 1, 2, 3, 4. So this is, I can say this, because this one has to be covered anyway. This is standing out separately. The most efficient way would probably be not covering anything more than once is the most efficient way, right? As long as you can cover one more than once, if it can result in a smaller group. If something is not going to result in a smaller group, there is no point in covering a one more than once. So in this case, there are only two ones. This is going to be a group, this is going to be a group, this is going to be a group. All groups are having two ones. So there is no point in unnecessarily doing this and doing this. So this is what I would, this is how I will write this. Three groups of two ones each. And what would this be in terms of the variable, in terms of the expression, product expression? So F would be sum of these products, 1, 2, 3. This would be A C bar D. Then this will be B C D. This would be A bar C D bar. Now, instead of doing this way, suppose I marked it slightly differently. Let me rewrite here. Suppose I put like this. Suppose I did it like this, because it's obviously not the most efficient way. You can see that because it's a small map with a few ones. But in general, when you have a large map with large possible groups, you may miss out and may do things like this. I brought this up to explain some of the definitions we gave in the last lecture. I talked about implicant, a prime implicant, and an essential prime implicant. An implicant is any group of ones is called an implicant. A prime implicant is the largest possible group of ones in the given group, of course. That cannot be an essential prime implicant. A prime implicant is a group which cannot become part of another implicant. An essential prime implicant is one which I said, if you remember, has at least one entry of 1 not covered in any other prime implicant. So this way here, this is an essential prime implicant. I will call this 1, 2, 3. This is 1. 1 is an essential prime implicant because this one cannot be covered otherwise. 3 is an essential prime implicant because this cannot be covered otherwise. Now, is 2 an essential prime implicant? Is 2 an essential prime implicant or not is the question. Do you think 2 is an essential prime implicant or not? The way I draw it, it is an essential prime implicant because these two ones cannot be covered anyway. But when I draw this map, there are two ways of combining these two ones. This is an essential prime implicant. This is an essential prime implicant. Is this a prime implicant? What is a prime implicant? The largest group of ones possible within that. This is the largest possible group of ones. So all the four here, I will call this 1, 2, 3, 4. Here all the four are prime implicants. Here all the three are prime implicants. But 1 and 3 are clearly essential prime implicant. 2 is not an essential prime implicant. It's a non-essential prime implicant for the simple reason I can cover these two ones in two other ways. So in this case again 1 is an essential prime implicant, 4 is an essential prime implicant, so 2 is a non-EPI. For the reason that this one could have been combined with this, I could have made a small, is an essential prime implicant. I could have covered this one to make another prime implicant. So it is the only way in which I can make a prime implicant, 1 is required, otherwise that 1 gets left out. Only then it is an essential prime implicant. We are not talking of the most efficient way here. Remember that I am only talking about definitions. Just because it is an essential prime implicant does not mean that it will be the most efficient way of doing it. So this is a non-essential prime implicant, this is a non-essential prime implicant because this one could have been combined with this to get another term, this 2 in this case. This term could have been combined with this term to get another term, just 3 in this case. So this is non-essential prime implicant. But the same argument, 1 and 4 are EPIs, and 2 and 3 are non-essential prime implicants. But having drawn this, in this case f is equal to 1 or 2 or 3. In this case f is 1 or 2 or 3 or 4, and all are 2 terms, 2 ones, all are 2 variables, 3 variable terms. There are only 3 terms in this case, 4 terms in this case. Evidently, it's very evident, it's obvious that this is less efficient simplification compared to this, but the fact remains that there are some non-essential prime implicants that has to come into the final expression in order to complete the expression. This is a very clear case of a non-essential prime implicant inefficiently used. In this case a non-essential prime implicant has been used efficiently because it was very clear and obvious, apparent just by looking at the map. Sometimes there may be 2 essential non-essential prime implicants, each of them can lead to the final solution which is correct, and both of them may have the same simplicity or the complexity, which case you have to choose between one or the other of the essential prime implicant, which case the choice is not unique. In this case the choice is almost unique. I would not choose this against this if I want to reduce if my aim is to reduce the logic, which is the aim we have been proclaiming. I will not go for this. But I will give you another example where I could have combined it 2 ways, both of them resulting in a same simplified expression in terms of number of variables and number of terms, involving a non-essential prime implicant. That will be an interesting case. So we will take another example. For a change, I will call this W, X, Y, Z. And this is my map. So what is the map now? F is sigma m 0, 2, 3, 5, 7, 8, 10, 11, 14, 15. Is that right? These are the minterms for which the output is true, for all the minterms output. I just do the map and then wrote the minterm. Normally it is the other way. Normally you are given the minterms for which the output is 1 from the truth table or from the problem description, word description of the problem. Either a word description of the problem or a truth table is given to you which will tell you what are the minterms for which the output is 1. Automatically the other outputs are 0. But in this case, just to illustrate a point in terms of implicants, prime implicant, essential prime implicants, non-essential prime implicants, I am just taking maps to give you examples. So I have to first draw the map and then tell you what are the minterms which are present in this map, which are true in this map. Now, what are the different ways of combining? You want to again efficiently, we have to do it. We have to make smallest possible number of prime implicants and make a combination which is the minimum possible combination. So now this one together form a group, a prime implicant, because they roll over top to bottom and left to right. So I will call this first prime implicant. I said the other day the adjacency, this cell is adjacent to this cell as well as to this cell. This cell is adjacent to this cell as well as to this cell. This is adjacent to this as well as this, and so forth. So all the 4 cells are adjacent to each other, very similar to something like this or something like this. So that is, and this is an essential prime implicant because this one would have been left out otherwise, or this one for that matter, because I could have combined this similar way but not this. I could have combined this but not this. So this, because of these two ones being present, this becomes an essential prime implicant. An essential prime implicant has to necessarily find its place in the final expression. The debate is only about how many non-essential prime implicants should be included to keep the function minimum, at the same time not omitting any one in the table. That is the only thing we have to be concerned with. Now, this one again has to be combined. There is no other way I could combine this one except this way. Is it not? Otherwise this one gets left out completely. Right? So I will call this 2. This is 2. Now I have 2 options. I can combine these 4 into an essential prime implicant. In fact, I should combine this way because this one would be left out otherwise. Of course, I can always combine these 2. These 2 combining is not a solution because a prime implicant is one which absorbs smaller implicants. So I put this one is not a solution because when I have a 4 larger prime implicant, I cannot put this one as an implicant. So I have to cover this. So this is an essential prime implicant for the simple fact this one will not be covered otherwise. So this will be number 3. Now the only one that is left out is this one. In order to complete my simplification procedure, I have only one uncovered one, and that one has to be included. So this, I can do it 2 ways. I can do it this way. I will call this 4. These 4 ones are adjacent to each other because this adjacent to this and so forth. Or I could have combined these 2 ones and these 2 ones. So, either this way or this way. These two ones. Now, this one was what was left out, remember, this midterm number 3. Midterm number 3 is what was left out. I had to include it. In order to include it in a largest possible group of ones, I can do it this way or I can do it this way. This one I will call 5. Unlike in this case, where we had an option which is less efficient, obviously less efficient, we have now an option in which 1 is essential prime implicant, 2 is essential prime implicant, 3 is essential prime implicant because of these individual things, 4 and 5 are non-essential prime implicant because there is essential prime implicant is 1 in which at least one unique one is covered in that group. No other way you should be able to cover that one. That is not the case with 4 and 5 because if you think of this one, that can cover this way or this way. So every one of these one can be covered. This one, all these other 3 ones have been already taken care of. In this case, all these have been taken care of except this one. This has been taken care of. This has been taken care of. Everything other than this has been taken care of. So this one can be covered either this way or this way. So when 4 and 5 are 2 options of covering this midterm represented by this 3, then it is not an essential prime implicant. 4 and 5 are not essential prime implicants. Sorry, non-essential prime implicants. So 1, 2, 3 are EPIs. 4 and 5 are non-EPI. But it is enough if one of 4 or 5 is included, because 4 or 5 cover, the 4 and 5 both cover this one which has been, this is the only one which is uncovered. After considering 1, 2 and 3, the only entry in the truth table which was not covered in our simplification was this entry, which will be covered either by this or this. Both 4 and 5 can cover one, this one. So where is the need for both of them to be present? And it does not either, the choice is not easy because both are of same complexity. This is 4 ones, this is also 4 ones. If one is 4 ones, the other is 8 ones, the complexity is different, so you know what to choose. But both are equal complexity, where is anything to choose from? So now I can write the final expression as 1 or 2 or 3 or 4. This is one option, or this R is English R, not the operator R. 1 or 2 or 3 or 5. This explains to you a non-essential prime implicant and its role in the final simplification. So I wanted to bring about the definitions of implicant, prime implicant, essential prime implicant and non-essential prime implicant, and the role of non-essential prime implicant in simplification. It is not that they are trivial, they can be ignored. They are essential sometimes, so you have to include it. But how many of them you include and what are the non-essential prime implicant you will include depends on your overall goal of minimum sum of products. Minimum sum of products. Okay, so I don't want to rewrite this. You know what each one of this. You can complete this. I wrote 1, 2, 3, 4, but 1, 2, 3, 4 are variables of or product terms with variables A, B, C, D, or in this case what? W, X, Y, Z. So 1, 2, 3, 4 and 5 are each product terms of variables W, X, Y, Z. You write it and finally you get the simplified minimum sum of product expression. Now we can have a 4 variable map. What is meant by this? Let us do this. For example, we did this because we started with simple gates and we drew a simple structure using gates and wrote an expression and then said we will write a truth table for that expression, and we wrote the truth table, found out the truth table had many more entries than the original circuit had. So we tried to see why, and we saw that the simplification of the truth table resulted in a smaller circuit that we started with, and we said simplification is possible using either Boolean algebra, which we saw, or by mapping method, which we have seen. So let us go revisit that and see now. We will do the reverse now. This is the sum of product expression you are given. There is a variable, a system of 4 variables. W, X, Y, Z, having an output F, circuit or system, has the following Boolean functionality as a functional relationship between input and output given by this Boolean identity, Boolean equation, not identity, Boolean expression, this Boolean expression. This Boolean expression gives the relationship between F and A, F on the one hand the output, and W, X, Y, Z on the other hand as inputs. What will it look like? We will see, because we have simplified this. So for that I need to expand this 1, 2, 3, 4, 5. Quickly we will do that. We will take this. We have no reason to choose this or this, so we will go with this. So let us quickly write what is 1. 1 is these 4 ones. What is the expression in terms of W, X, Y, Z? This is X bar, Z bar. 1 is X bar, Z bar. 2 is what? These 2, right? W bar, X, Z. X, Z. 3 is this, which is W, Y. And 4 we are going to take instead of 5, so 4 is what? This 4. That would be YZ. So my expression is then X bar, Z bar, W bar, XZ, WY plus YZ. These are gates with inputs X and Z, of course inverted, W, X and Z, W inverted, W and Y, Y and Z. These are 4 AND gates. Outputs of these 4 AND gates tied together by an OR gate. That is what the circuit is. Circuit is going to look like this. So we have X, Z, is X again, W, Z, the second term, third term is WY, and fourth term is YZ. Z has to come from here, which is here. So if you don't want to lose track of these inputs, you can write it one more time here. YZ, WY, this is Z, W bar X. Okay. X, W bar Z. This is W bar Z bar, X bar Z bar. all of them combined in an OR gate with 4 inputs. This is the function which we are trying to. This function represented by this circuit whose corner map is this and whose functional description is this. Of course, I can already write the truth table. Truth table is only an expansion of this. I will have to put x, w, x, y, z, all the 4 combinations 0, 0, 0, 0 to 1, 1, 1, 1, and then put here finally 1 and 0. So it requires 3, 2, actually 1, 2 input, 1, 3 input AND gate, one 3 input OR gate. Oh, I'm sorry, 4 input OR gate, 3 2 input AND gates, and how many inverters? 2 inverters. 2 inverters. 2 or 3? 3 inverters. This is inventory. You have to ask for these components in order to build a circuit, and it will work. And you can now associate with W, X, Y, Z some signals, as you did in the example previously about some system which is to represent a particular condition. W, X, Y, Z may be 4 parameters you are monitoring, and on this incidence of the parameters in this particular way will trigger an event at the output of this system. That could be an example of the use of this. So you go for a definition of the word description of the truth table and the Boolean relationship, mapping, and then simplification, drawing the circuit, and then of course you have to get the components, build it and test it. Now the variables x, y, z, we have used 3 or 4 w, x, y, z, and then for 5 we may have used, 6 we may use, 7 we may use. Systems, digital systems today are very complex. A system like a microprocessor, a system like a controller, a system like a automotive system or a fuel injection, or even very, very complex systems like missiles. I already told you, missiles and aircraft, things like that. So I don't think we can work with 3 variables, 4 variables. 3 variables, 4 variables are classroom exercises. What will happen if the variables are more than 4? We have already represented a 2-dimensional. Now it has to go 3-dimensional. If we have 5 variables, what do I do? So let us say we have a 5 variable map. Five variables, let us call these variables A, B, C, D, E. I can only represent 16 cells in a 4 variable map, 2-dimensional, and 5 variables will have how many min terms? 32, 2 power 5. So we need to have one way to have one variable. See, the variables, if we start listing them as truth table, it will become starting with 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, and finally it will become, this is min term 0, min term 1, min term 31. I told you we will have to start always with 0 min term and go on till the last min term, which is 2 power n minus 1. 2 power 5 is 32, minus 1 is 31. So 0 to 31 will be min terms. So one way to do this would be draw 2 maps considering only 4 of these 5 variables each. leave the A out because first 16 entries of this truth table, M15 would be 0, 1, 1, 1, 1. M16 would be 1, 0, 0, 0, 0. So these entries will have A is equal to 1. These entries will have A is equal to 0. Isn't that? First 16 entries of the truth table will have A is equal to 0. Second 16 entries will have A is equal to 1. So I will draw this map with variables B, C, D, E, always remembering A is equal to 0 in this map. Likewise, I will do B, C, D, E one more time, always remembering A is equal to 1 in this map. Now, the minterms will be M0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. So whichever minterm is 1 output, you map it in the map in the corresponding cell, either here or here. If it is the minterm corresponding to terms between 16 and 31, the 1 will appear here, so it will go in this part of the map. So you can map it the way you would map the 4 variable map graphically, but while reading you have to be careful. The adjacency works between these two maps. The 1 here and the 1 here are considered adjacent because the only variable different from these two maps, this is B is equal to 0, C is equal to 0, D is equal to 0, E is equal to 0. This is also B is equal to 0, C is equal to 0, D is equal to 0, E is equal to 0. If I have 1 here and a 1 here, the variable A is 0 here, variable B is 1 here, A is 1 here. So these two cells are adjacent. Cell number 0 and 16 are adjacent, right? So a corresponding cell in this map and this corresponding cells in this map and this map are identical, or are adjacent. That property has to be built in when reading the map. That's all. So I map the entire variable. So we'll use the same arbitrary thing. We'll do this 0 to and this for change I will put here okay. Now these 4 ones which we called prime implicant 1, essential prime implicant 1 here will appear here also in both the maps. So this I will call 1, including this. These two together are 1. Now these 4 again, I don't know what we called it here, we called it 3, but don't worry about it. This and this are again common between these two maps in the same cells, so we'll call it 2, this and this. Now what is left out? These 4 are left out. I'm going to combine this way or this way, doesn't matter. Okay, I will combine this way. But this is not common to this map. 1, 1, 1, 1 here is unique to A is equal to 0, not to A is equal to 1. So I am going to call this 3, in which I will have to appear, make A is equal to 0 in that. This one is unique to this map and not to this map. So this is 3, these two ones I will call it 4 because this is not here. This one is unique to this, not to the other map, so 5. So there are 5 prime implicant, all essential. I made sure that simple because it's an example. With 5 variables, I wanted to drive home the point of how to simplify a 5 variable map. So I made them simple, essential, all of them essential prime implicants, so we don't have to worry about non-essential prime implicants and proper choice of that. So we have 5 PIs, EPIs, 1, 2, 3, 4 and 5. We should know how to now see actually writing the expression minimum sum of product expression based on this is called reading the map. Somehow they call this reading the map. So we should be able to read the map now. They use the term reading the map. After putting all these ones and grouping them, essentially identifying them as groups, you writing the final expression, that operation is called reading the map. So now I have to read the map to get 1, 2, 3, 4, 5 and then put it together as one expression of F in terms of A, B, C, D and E. Okay? So what is 1? Quickly, 1 is already we have said was 1 was here this is okay. This is C prime, E prime. Since this is common between two, A is equal to 0, A is equal to 1. So 1 is C prime, E prime. That right? Or C bar, E bar. Want to call it C prime, E prime, C bar, C, E bar. Or not C and not E, whatever. 2, again common between these two maps. That would be B, D. Comes the third map, third EPI. Third EPI is this, between these 4 cells, which is DE. But this is not available here, so I will have to include the information. It is only available in the A bar part of the map. I will have to make sure that you know it is on A bar part of the map and not in A part of the map. So I have to say A bar and DE. So 3 is A bar DE. 4 is again only for this map, A bar map. 4 is this prime implicant, essential prime implicant, which is B bar C E. A bar B bar C E, but you have to add a bar to that. A bar B, A bar B bar C E. It would have been read as B bar C E, but it is part of, it is available in the, it is found in the A bar part of the map, so it is A bar. And finally, this 5th prime implicant in this part of the map, A is equal to 1 part of the map, which is B C E with a A. Okay? So now my final expression, if you want to, you can write it as C bar. I don't know whether you want to really do it. You can do that. That would be C bar E bar BD A bar DE A bar B bar CE and you can draw your gate structure or whatever. This is how we read a 5 variable map. Identify the common cells. Of course, some people draw it next side by side, some people draw it together, left and right, and then you somehow it is only it's not a mathematical procedure or anything. It is a convenience. Whichever you feel comfortable with, do it. Now I can extend this to 6 variables, can I? Yes. Which I want 6 variables, I want 4 maps, each of 16 cells. I'll have to say 6 variable map. A bar, B bar, A bar, B, A B bar, A B. So min term 0 to 15, 16 to 31, 32 to 47, 48 to 64, and then you have to adjacency, all sorts of adjacency. You have to adjacency between these, adjacency between all the 4, all that. And you can go on writing the expression and have fun, unlimited fun. Like all these checker games you play. But the limitation, why I am saying all this is because there is a limit, beyond which, after 6 how will you do? Of course you can always find a method of doing it, and then it becomes inefficient. We started with the map method because of its simplicity and efficiency. Then we are reaching a point where the simplicity is lost. It will become an ordeal. So beyond 6 variables, 5 variables is most comfortable. 4 is good. We like to have a problem with 4 in the exam, maybe 5, manage. 6 is okay, but 7 and above become cumbersome. So now what we have done is, after all this is a procedure, what we have done is adjacency. Find ones which are adjacent to each other when you represent it as a graphical, in a graphical way. So it's always possible to write a computer program to find out the adjacent ones in a truth table and keep on repeatedly doing it. So the computer, the advantage or the problem, whichever way you see it, the computers you have to do it step by step. Combine 2 ones at a time, not more than 2 ones at a time. It's too much to handle for computers. Put 2 ones at a time, and then when 2 ones at a time will become 1 1, then you say 2 more, 2 2s. And so keep on giving it in steps. So write a program, an algorithm they called it. So algorithm is a step-by-step program. You write an algorithm or a program to systematically find out all the ones in a truth table, merge them to the best possible way, and repeatedly do this. Sometimes you may have to finally look at there may be several terms in which we may have to, some redundancy may be there, the question of essential prime implicant, non-essential prime implicant, that computer cannot resolve, After all, computer is what you program. Computer cannot be more intelligent than you are, because you are the one who put the program in the computer. If the program is limited by your intelligence, cannot be more than your intelligence. So finally we may have to intervene some place and say we will list all the essential prime implicants and non-essential prime implicant, make a choice of the right combination. That we may have to do. Such a method is called a tabulation method as against the map method. We will not do that, but I thought I should tell you. So if the number of variables become extremely large, go for what is known as the tabulation method. These are computer based methods. Of course you can also do it by hand to understand the algorithm. So you get same example of 31 cells or even 63 cells you can take for fun, 64 cells, 0 to 63, or even 31, 0 to 31. Do it the way the computer would do it. Combine 2 at a time and then like that. Just to get an understanding of this method. I am not going to teach this in this class, but it's available in many books. Talk about this method called tabulation method. Some people call it prime implicant method. Some books call it prime implicant method. Some books call it graphical method, the tabulation method. So as a reading you can do that to understand the concept behind this, but it is all computer programs, very easy to understand once you know how it works. So you can do a simple example of the same example we do in the class. Try to do it using this method so you'll have an understanding of this program. We'll stop here for today.